Hello everyone. Today I'm presenting my work on inter-domain alignment for predicting high-resolution brain networks using teacher-student learning. This work has been done at Basira Lab by myself, Ala Besadok, and supervised by Dr. Islam Rekik. Multi-resolution neuroimaging has spanned several neuroscientific works thanks to the rich and complementary information that is crucial for early disease diagnosis. Accurate and automated super-resolution image synthesis has the great potential to circumvent the need for acquiring high-cost medical scans and time-consuming preprocessing pipelines. So, the problem that we aim to solve is, for given a low-resolution brain graph belonging to some modality, how can we predict high-resolution brain graph that represents another modality? For instance, from morphological connectivity that derive from T1 weighted MRI to functional connectivity that derive from resting state fMRI. To solve this problem, there are some landmark works encoding machine learning-based models to SuperResolve Brain Graphs. One of them uses manifold learning to learn how to select best samples for superresolving brain graphs. Another method adapted a template-based learning to predict high-resolution graphs from low-resolution graphs. But since they were designed in a dichotomized manner, there are agnostic to cumulative errors that are important for clinical forecasts. To overcome this issue, geometric deep learning work has been proposed. Also, this work further developed by adding an adversarial loss to align the predicted high-resolution brain graphs with the ground truth ones. However, they are incapable of working on different modalities. As a shared limitation, previous works overlooked the handling of domain fracture problem between the low and high-resolution domains. To overcome these issues, we propose L2S KDNet, an architecture based on teacher-student paradigm that provides lower computational costs and allows for deployability in real-time applications. We introduce a topology-aware adversarial loss function that preserves both complementary topological properties of SuperResolve Brain Graphs. We design a discriminator that provides inter-domain alignment for brain graphs. As an overview, our framework can be split up 3 steps. First, we perform feature extraction from multi-resolution brain graphs. Then, our teacher network learns to predict low-resolution brain graph embeddings and high-resolution brain graphs. After that, teacher network displays its knowledge to the student network. Thus, we reduce the computation cost of teacher network by encompassing a large number of its parameters and make network affordable. Now, we will have closer look to each of the components. Firstly, since the brain graph is represented by a similarity matrix, we vectorize its upper triangular part, then we stack resulted vectors in a feature matrix F. The question is that, given a low-resolution brain graph, how are we going to obtain this high-resolution brain graph representation? So, we formalize it as a graph autoencoder problem. First, we have an encoder that maps low-resolution brain graph to lower dimensional space called embedding. And then we have a decoder where we perform super-resolution operation for given embedding. Also, in order to enforce the encoder to learn an inter-domain alignment, we design a discriminator that is GCM-based network. Moreover, in order to preserve the unique topological properties of brain graphs, we further regularize our network using a novel topology loss that is composed of local topology loss that aims to preserve local graph structure which reflects the node importance in the graph, and global topology loss that aims to preserve the global graph structure such as the number of vertices and edges. As next, our student networks learns the knowledge of the aligned brain graphs as well as the topological structure of the predicted high-resolution graphs transferred from the teacher. We leverage the decoder of the teacher to optimize the student network. By this TD regularization, we are bringing predicted high-resolution graphs closer to prediction of the teacher network. As a result, we obtain a network that super-resolves brain graphs with low computational costs thanks to the knowledge distillation. For testing our framework, we use 276 subjects from the SLIM dataset. Each subject is represented by a morphological low-resolution brain graph and a functional high-resolution brain graph. For the evaluation, we use a threefold cross-validation technique for testing our student network. We benchmark our framework against 4 different comparison methods. Firstly, we tried a teacher-student architecture without any intermodality alignment. After that, we add a discriminator to the decoder of the teacher for distinguishing between predicted high-resolution brain graphs and the ground truth ones. And also, we tested by removing some losses from training process of our proposed network. We benchmark our network without using local topology loss and without TD regularization. That means we remove the teacher's decoder from the training process of the student network. To test our student network, we use different evaluation metrics by comparing ground truth high-resolution brain graphs and predicted ones. Our network achieved the best prediction performance across all benchmark methods when using global topology, which is MAE between ground truth and predicted graphs, and node strength evaluation measures. And it ranks second best in MAE between the eigenvector and PageRank centralities. Because they capture more complex topological patterns of the brain graph, it's difficult to preserve compared to the global topology and node strength. In conclusion, in this work, we introduce a teacher-student framework designed for a brain graph super-resolution based on interdomain alignment learning. We contribute studies with proposing domain-aware teacher network based on graph autoencoder and a novel topology-aware adversarial loss function. In our future work, we will generalize our framework to a multi-resolution brain graph synthesis test and work on early disease diagnosis. Feel free to check our recent review paper on GNNs in network neuroscience covering recent GNN architectures for brain connectivity integration, classification, super-resolution, and more. You can also visit the GitHub repo of the paper. For more, please visit us at basira-lab.com.